Hello everyone, we are excited to present our project title, Language Models are Unsupervised Multitask Learners, which is the original research paper that introduced GPT-2. GPT stands for Generative Pre-trained Transformer. GPT has become one of the most influential architectures in modern AI, especially for language understanding and generation. In this presentation, we are walk you through how GPT-2 work, what makes it different from earlier models, and how we implement it and train our own version from scratch. Let's start by looking at the key ideas behind GPT-2. In the early days, many models follow a two-stage process: pre-training on large unlabeled text data to learn general language patterns, and then fine-tuning on small labeled dataset for specific tasks like translation or classification. GPT-1 also followed this approach. It was first pre-trained on large amounts of unlabeled data, and then fine-tuned for each downstream task. For each task, such as translation or question answering, an additional output layer was added, and the model was fine-tuned using task-specific labeled dataset. But it's too narrow. Its fine-tuned model was highly specialized. For example, a model fine-tuned for translation performed poorly on other tasks like question answering or classification. This motivated the development of GPT-2, a more general-purpose language model that aims to solve multiple tasks with just one model, without the need for fine-tuning. GPT-1 was only trained for predict the next word in a sentence. It learned patterns but couldn't perform specific tests. But GPT-2 can translate "I like you" to "좋아해" just by seeing the prompt "I like you" translate to Korean. Instead of adapting to tasks through fine-tuning, GPT-2 can handle downstream although it was never trained for translation. This is called zero-shot learning. Because the model is trained using only unlabeled data and no fine-tuning step is required, it becomes a purely unsupervised learning system. This is arguably the most important takeaway of the GPT-2 paper. Pre-training alone, if done at a large enough scale, can enable general-purpose task solving without task-specific supervision. Let's break down the architecture of GPT-2 and see how its components work together to generate language. You first need to look at the fundamental concept behind language modeling, the autoregressive model. The core idea is that current values are predicted based on a linear combination of past values. This is formally expressed as the joint probability of a word sequence. This is how autoregression works in practice. We generate tokens one by one, and at each step, the previously predicted token is added back into the input and used to predict the next one. This iterative generation process makes autoregressive models well suited for sequence generation tasks. The most successful implementation of the autoregressive modeling is the transformer architecture. GPT is based on the transformer, but with one key difference. Instead of using both the encoder and decoder, GPT uses only the decoder blocks because its main goal is to generate text. The GPT model stacks multiple decoder blocks to transform the input into output. Each decoder receives the embedded input and passes it through several layers to generate the next token. Each input token is encoded using two sources of information. First, token embeddings. Token embedding converts each word into a vector that captures its meaning. But meaning alone is not enough. For example, Rose loves Jack and Jack loves Rose have the same tokens, but their order changed the meaning completely. So the model must also know where each word appears in the sequence. The second input is positional input encoding. It gives each token a sense of where it appears in the sequence. These two vectors are added together to form the final input vector. Now, let's zoom into a single decoder block. Each decoder contains three main components: masked multi-head self-attention, feed-forward neural network, and add and layer norm. One of the most important components here is the masked multi-head self-attention layer. This is where the model learns context by looking at previous tokens. This attention mechanism allows the model to capture the relationship between words. And by using multiple attention heads, the model can look at different type of relationship in parallel. What makes GPT autoregressive is the masking in self-attention. In GPT, we apply a mask so that each position can only attend to the past and present, ensuring the model cannot cheat by seeing future tokens. Finally, after passing through the decoder stack, the model produces an output vector. This vector is then multiplied by the token embedding matrix and produces a score for each possible token. The scores are passed through a softmax function to convert them into probabilities, and the token with the highest probability is selected as the next word in the sequence. Let's walk through how we re-implemented GPT-2 from scratch, including design choices and challenges we faced. We trained the smallest GPT-2 variant as defined in the paper. As specified in the paper, we applied weight sharing between the token embedding and the final projection head, and followed the updated design with pre-layer normalization. Regarding the dataset, we used the FineWeb corpus, a high-quality filtered web dataset that is tokenized and stored as NumPy shards. We sampled 10 billion tokens for training. We set a batch size which closely matches the 0.5 million tokens used in the paper. We trained the model for 19,000 steps, which correspond to one full pass over the 10 billion token dataset. Our optimizer is ARAM-W with the typical hyperparameters used in LLM training. We also followed the GPT-3's training strategy. To speed up training, we used TDP across 8 800 GPUs. We were able to complete training in just about 2 hours and a half. Here's a look at our training and validation loss curves. You can see a sharp drop in loss during the first 3,000 steps, followed by a smooth and stable convergence of afterwards. Importantly, the train and validation losses remain closely aligned, indicating that no overfitting occurred during training. Our final validation loss reached 3.3, which corresponds to a perplexity of about 27, a reasonable results given the limited training budget and model size. Let's take a look at our first set of experiments. We evaluated our model on the Lambda dataset, which consists of passages where the final word can only be predicted by understanding the full context. Accuracy is measured as the percentage of exact matches. Our model achieved 16%, while GPT-2 Small reported 45%. Note that the original paper excluded stop words, which increased accuracy by over 10 percentage points, so this may partially explain the gap. Now, dive into our second round of experiments. We also evaluated our model on the CBT dataset, where the goal is to choose the correct word to fill in the blank from 10 candidates based on the surrounding context. Our model achieved 72% accuracy on common noun tasks and 51% on named entity tasks, compared to 87 and 83% by GPT-2 Small. Named entity tasks are especially challenging, requiring deeper understanding of character and context. Despite the domain gap in our training data, our model shows reasonable performance. Let's analyze why our model didn't perform as well as expected and explore what factors may have contributed. In both evaluations, our model underperformed compared to GPT-2 Small. One key reason is insufficient training. GPT-2 was trained on 40 GB of data over 2 or more epochs, whereas our model was trained on 10 billion tokens for just one epoch. This difference in total optimization steps likely contributed to the performance gap. Another key factor is the different characteristic of test data and evaluation data. Our model was trained on FineWeb which consists of structured, factual, and education contents, mostly expository in nature. In contrast, Lambda and CBT are based on novels requiring understanding of dialogues, character relationship, and narrative context. This domain gap makes tasks like Lambda and CBT, especially any questions, much more challenging for our model. To verify our GPT-2 implementation, we loaded OpenAI's official pre-trained weights into our custom-built architecture. As shown in the results, our model achieves performance close to the original paper, especially on the Lambda benchmark for GPT-2 XL. This confirms that our GPT-2 architecture is structurally correct and faithfully reproduces the original design. To wrap up, GPT-2 is introduced as a zero-shot unsupervised language model that performs various tasks without task-specific fine-tuning. We re-implemented GPT-2 Small in PyTorch and trained it using DDP. We then evaluate the model on Lambda and CBT to assess its zero-shot performance. Although our trained model showed lower accuracy due to limited training, we confirmed that our architecture is correct as it achieved results close to GPT-2 when loaded with pre-trained weights. This validates the fidelity of our GPT-2 reproduction, both in structure and functionality. Thank you for listening.